Good evening, everyone. Are you all able to hear me?
Yes, ma'am. Good evening, ma'am.
Yeah, good evening. So I think let's start today's sessions. So before going to the session, let me introduce myself. I am Harsha from IIT Tirupati. So today we will be covering the week 5 problems, means the concepts, the problems related to the concepts covered in the week 5. So in the last week, actually, we started linear algebra. Until week 4, it was actually the basics of abstract algebra. And now we started the linear algebra. So the very basics we have studied. So first let us just go through what are all the concepts covered in the class. And then we will solve some sample problems, which is similar to your assignment problem, which will help in solving the assignment problem. So if you have any doubt in between, you can ask, and please unmute and ask. All other time, please mute yourself, and please turn off the video also, so that we can have a very smooth class. So first, let me share the screen. Is my screen visible now? Excuse me, is the screen visible?
Yes, ma'am.
Okay. So, what are all the concepts that covered in the last week? First of all, we started with the vector spaces. Okay. So I'm not going to the very details, and I'll just go through the concept what are all covered. So I hope you have already gone through the videos. So we have seen what is a vector space V with operation addition and multiplication. That is vector addition and scalar multiplication over a field F. So there are some conditions to be satisfied in order to be this V is a vector space. And next thing we have studied is subspace. Subspace of a vector space. Okay. So and some condition for a subset to be a subspace of a vector space, like when a non-empty subset will be a subspace of a vector space. The condition for that also we have studied. So while going through the problem, we will recollect that and we will use those theorems. Okay. Linearly dependent set and linearly independent set. And what is a span? By span of a set. So I hope you all know this concept. And
allow Zoom to find the connect to determine the relative position of nearby device. In the reason, allow Zoom to find the connect to and determine the relative position of nearby device. Hello.
Excuse me.
Hello.
And then we studied what is a basis. What is a basis of a vector space? And we have studied, like, depending on the basis, we have studied whether a vector space is finite dimensional or infinite dimensional. If number of elements in the basis is finite, then the vector space is a finite dimensional, and otherwise it is an infinite dimensional. Okay. and some theorems related to this. And dimension. So I already mentioned dimension. Okay. So these are all the concept we have gone in the week 5. Okay. So now let's go to the problems. So the first question is to find the dimension of a subspace of a given vector space. So let's see. Given a vector space, let V be a vector space of 2 by 2 matrices over R. What does this mean? It contains all 2 by 2 matrices whose entries are coming from the real numbers. Okay. And W be the subspace of symmetric matrices. The question is to find the dimension of W. And the options are 2, 1, 3, and 4. Okay. So given the vector space of the set of all 2 by 2 matrices, and W is a subspace of this vector space V, which contains all the symmetric matrices. So can anyone say what is symmetric matrices? What is mean by symmetric matrix? What is a symmetric matrix? Symmetric matrix means A transpose equal to A. A equal to A transpose. So for a matrix A, if the condition A equal to A transpose is satisfied, then we will call it is a symmetric matrix. So A transpose means just interchange of A and rows and columns of the matrix A. Okay. So before going to the dimension of the symmetric matrices, let us see about this vector space. Okay. Here the vector space is set of all 2 by 2 matrices over R. So how can we write the vector space V? V means set of all A, B, C, D such that A, B, C, D are elements from the real numbers. Clear? Okay. First of all, is this a vector space? We have some condition for a set to be a vector space. Okay. So is this a vector space? Can anyone answer? Am I audible to everyone? Okay. So the first thing we need to check, like first of all in the question it is given it is a vector space. So in order to be familiar with this concept, you can check whether V is a vector space or not. So I'm not going to all the details. So the thing is we need to check V under addition is an abelian group that we can check. So if we are taking two matrices, the addition, the sum of two matrices is again M matrix in V, right? And that addition, matrix addition is commutative, associative, and the identity 0, 0, 0, 0. The 0 matrix belongs to V, and for any matrix A, minus A is the inverse of the matrix. So V plus is an abelian group, and under multiplication, that is under scalar multiplication, we have so many property. That means like for some scalar C and matrix A, CA is also in V, okay, for C in R and A in V. And what are all the other property we need to prove? That C1 plus C2A. These are all just very trivial results. C1A plus C2A and C1 C2A equal to C1 C2A. Okay, and 1 into A equal to A. Okay, so one is the identity here, sorry, identity matrix here. Okay, so just go through the what are all the conditions to be a vector space and just verify all the things. So V is a vector space. Now, what is our subspace given? Subspace W is the set of all symmetric matrices. Okay, W equal to set of all symmetric matrices. Clear? That means set of all A in V. That means we are collecting all elements from the above defined vector space V such that A equal to A transpose. Okay. A equal to A transpose is the condition of symmetricity. Okay. And it is a subspace of V. First of all, it is a subset of V, right? So the all elements of W comes from V such that A equal to A transpose. It is the symmetric matrix. Okay. Now, we need to first verify W is a subspace. So, do you remember what is the condition to check the subspace? Like we had a theorem in the class. A non-empty subset W of a vector space V is a subspace if, anyone remember the condition? What is the condition? Like a vector space V we are having and a non-empty subset W we are having, and this W is a subspace of V if anyone knows? The condition is A, or we can write it as in general, Cx plus Y belongs to W. Okay. For all scalar C, that is C in F, like V is the vector space over F. So for all C in F and for all xy in W. Okay. If this condition is satisfied, then we can say W is a subspace of V. Okay. Now we have one W here. We need to check whether this W is a subspace of our V is the set of all matrices. Okay. Now, first thing we need to check is whether W is non-empty or not. First of all, it should be non-empty. Then only we can go to this condition. Cx plus y belongs to W. Okay. So, is this W non-empty? Is the W non-empty? Anyone please? I want you to answer the questions also. Like, if you have doubts, you can ask. And like whatever the answer, even if it is wrong, please respond to my questions. Is this W non-empty? Like, does there exist any element in W? Okay. Okay. See, W is the set of all symmetric matrices. First of all, it is the set of all matrices, right? Now, let me ask one question, 0, 0. Does this belongs to W? Okay, this is very trivial question. Anyone can answer. Is this belongs to W?
Yes, ma'am.
Yeah, this is belongs to W because it is a 2 by 2 matrix. So it belongs to V first of all. And also the transpose of the 0 matrix is 0 itself. Okay. So A equal to A transpose condition also satisfied. So it belongs to W. Hence, W is non-empty. Now, to prove it is a subspace, what we want to prove that Cx plus y belongs to W for all C in F and xy in W. Okay. Here, x, y in W means x and y are two matrices. For example, we can take A and B. A, B be two matrices in and C, B, N is scalar. Okay, here the field is R. We have already mentioned the set of all, like the set of all 2 by 2 matrices over R, right? So the field is R. Okay. Now, what we want to prove that CA, to prove that CA plus B belongs to W. Okay. So this is the condition in theorem. If Cx plus y belongs to W for all C in F and xy in W, then this W is a subspace. So we have taken AB from W and C from R. We need to prove that CA plus B belongs to W. Clear? Now, this belongs to W. When we will say this belongs to W, we know that W equal to set of all A in B such that A equal to A transpose. That means for a metric to be in W, that metric should be symmetric, right? So here, to prove it is in W, we need to prove that it is a symmetric matrix. We need to prove that CA plus B equal to CA plus B transpose. Okay. If this condition is satisfied, then we are done that W is a subspace. Now, let us see. What is CA plus B transpose? What is CA plus B transpose? Like, we know the basic operations in matrices. We can just like split it, right? C times A transpose plus B transpose. You can just verify how it is coming. So CA plus B transpose will be CA transpose plus B transpose. Now, what is A transpose? What is A transpose and what is B transpose? Okay, yeah. A and B transpose is B. What is the reason? Since A and B belongs to W and W is the set of all symmetric matrices, correct? So what we will get is A transpose equal to A and B transpose equal to B. Clear? So we got CA plus B also belongs to W. Hence this W is a subspace of V. Okay. Now, our question is to find the dimension of this W. Okay. Before going to the dimension of W, let me ask a simple question. What is the dimension of V?
4.
Yeah, dimension of V is 4.
And also for W is 4. Answer is 4.
Dimension of W is 4. Okay, just think once again what is the dimension of W. First we will see what is the dimension of V. It is 4, correct? But the dimension of W is not 4 because W contains the symmetric matrices only. Like there are some matrices which is not in W but in V. So obviously the dimension of V is something greater than dimension of W, right? So just see how the element of W, how will be the structure of the element of W, and you can just check in between. Okay, before that, let me write what is the dimension of V. We know that V equal to set of fold A, B, C, D such that A, B, C, D in R. Okay. Now, dimension of V means the number of elements in the basis of V. So, can anyone say what will be the basis of V? Like there are different bases, but we have a standard basis in general. So, what is the basis of V? If we know the basis of V, we just need to check
Cardinality of W. Cardinality of W is a dimension of V.
cardinality of W. First of all,
Sorry. Basis of, I think, I don't know. The basis of V, the cardinality basis of V is the dimension of V.
yeah. Cardinality of the basis of V is the dimension of V. So basically, we need to find basis of V. So basis of V means a set of linearly independent set which spans whole V. Okay. So do you have any guess what can be the elements of basis of V? Okay. First, I am taking any element A, B, C, D in V. Okay. So we have here 4 variables A, B, C, and D. This can be any variable. This can vary in R. Okay. So if I am taking A outside and I am writing 1, 0, 0, 0 plus B 0, 1, 0, 0 plus C 0, 0, 1, 0 plus D 0, 0, 0, 1. I can write like this, right? I am writing A, B, C, D as the linear combination of 4 matrices. Okay. So here the first matrix covers all kind of matrices which have first non-zero entry and all others are 0. And this kind of matrices covers all the matrices in V which have this second 1, 2 entry is 1 or 1, 2 entry is all real numbers. Like all the linear combination we are taking means we will get here non-zero and all others 0. In the same way, all those kinds of matrices are covered. Like with the 1 non-zero entry, all others are 0. Okay. If we are taking all the linear combination, we can cover all the matrices A, B, C, D. Okay. So, if I am taking any matrix A, B, C, D, I can write this matrix as a linear combination of these 4 matrices. Clear? So, I am just considering S equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. I'm just taking all these four matrices here and just writing it as the set S. First of all, this S spans our V, right? Okay, that is what we have proved here. If we are taking the linear combination like this, span of S equal to the set of all matrices in V. Is there any doubt in this span of S equal to V? Is this clear? Span of S equal to the vector space V? Is this clear? If it is not clear, you can tell. And if it is clear, just answer yes.
Yes.
Okay. Now, what we want is basis. Basis means span of S should be equal to V and this S should be equal to linearly independent. Okay. Now, our question is S linearly independent? What do you think? Is this linearly independent or not? Any guess? Is this set S linearly independent or not? Any guess you can say, like, even if it is wrong, just say, like, what do you think?
The linear combination should be zero matrix.
Yeah, linear equal to 0, we will equate. And if all the coefficients are 0, then it is linearly independent. So what does linearly independent means? If I am taking C1 into 1, 0, 0, 0 plus C2 into 0, 1, 0, 0 plus C3 into 0, 0, 1, 0 plus C4 into 0, 0, 0, 1 and I am equating this to the zero vector. The zero vector here is matrix 0, 0, 0, 0. Okay, let me finish this. Okay, so linearly independent means if we have a set, we will take the linear combination and we will equate that to the zero matrix. Okay, and if we are able to prove that each of the C1, C2, C3, C4 are 0, then it is linearly independent. If at least one of the CA is non-zero, it is linearly dependent. Okay, now we are here checking whether it is linearly independent or dependent. So we equated this C1, the first matrix, plus C2, second matrix, plus C3, third matrix, plus C4, fourth matrix equal to the zero vector in the vector space. So we should check what is C1, C2, C3, C4. So here the left side, how we will get C1, C2, C3, C4. Okay. I'm just adding all this here. C1 plus 0 plus 0 plus 0. So first entry is C1. Here 0 plus C2 plus 0 plus 0, C2. And in the way, like third and fourth. So we are equating this to the zero vector, correct? So what we will get, like these two are equal means the entry wise it is equal. C1 equal to C2 equal to C3 equal to C4 equal to 0. C1 equal to 0, C2 equal to 0, C3 0, C4 0. So this linear combination is equated to 0 and we got all the coefficients CAs are 0. Therefore, S is linearly independent. Is this clear for everyone?
Yes, ma'am.
Yes, ma'am.
So we got a set S of 4 elements which is linearly independent and spans the whole subspace V. Okay, sorry, whole space V. So we got dimension of V. What is the dimension of V?
4.
4. Okay. Now we need to find the dimension of W. Okay. First, let me write the W. W equal to set of all A in B such that A equal to A transpose. Okay. If we are getting this W like this, like whatever the set we are getting, first we will take the condition and we will just expand so that we will get to know like what are all the requirements. Okay. Now here let A equal to A, B, C, D. Okay. So a random matrix I am taking. So this A is in W means A should satisfy A equal to A transpose. Okay. A equal to A transpose implies A, B, C, D equal to, we are interchanging the rows and column. Okay. So first row AB will become the first column and second row CD will become the second column. Okay. Now, from here, what we can say? A equals A, like which is obviously true. And here B equal to C and C equal to B. Okay. So second condition is B equal to C. And the last entry D equal to D. Okay. So for A to be in W, we need to satisfy these conditions. Here the first and third conditions are trivial, like it is satisfied always. Okay. The only thing we need to consider is this B should be equal to C. So how we should write? A equal to A, B, C, D. So A and D are unchanged. Okay. A and D exist there. B equal to C. So if I am fixing B, then C should also be equal to B. Okay. These two entries are equal. So what we are here getting is the only three variables A, B and D. These three variables are actually enough to determine the whole space W, subspace W. Is that fine for everyone? Okay, just looking this nature of A, can you say, like now here this A is an element in W. Okay, this is a general element in W. Now, just looking at this structure, can you say what can be the dimension of A?
3.
3.
W 3.
Yeah, dimension of W is 3 because only 3 variables are involved. So we can write it as AB CD equals, sorry, AB BD, okay, equals A into 1 0 0 0 plus B into 0 1 1 0, because here both the place it is B. So what we will get is B into 0 1 1 0 and plus D into 0 0 0 1, because here it is like this. Okay. So the three matrices 1 0 0 0 0 1 1 0 0 0 0 1. These three matrices is enough to span the W. Okay. Now let me write it as 1 0 0 0 0 1 1 0 0 0 0 1. So T spans W. T is linearly independent. Okay. Is this T linearly independent? Or do you think is this T linearly independent or not?
Yes, madam.
Yeah, it is linearly independent. Like if you have any doubt, as in the previous case, you can just check C1 into first matrix plus C2 into second matrix plus C3 into third matrix, which is equal to we are equating that to 0 matrix, and we can just solve and we can get the values of C1, C2, C3. So here C1, C2, C3 will be equal to 0, and so we can conclude it is linearly independent. If one of the C1 is not 0, CA is not 0, then it will be linearly dependent. T is linearly independent here. So just prove it as an exercise. Okay. Is there any doubt in this one? Anyone?
No, ma'am.
Okay. So in the same way, okay, we will just quickly go through the skew symmetric matrix also. Okay, now suppose X equal to set of all A in B. I'm taking all skew symmetric matrices. So what is the condition to be skew symmetric? Symmetric is A equal to A transpose. Skew symmetric means A equal to minus A transpose. So this is the condition for skew symmetricity. So in the same way, first prove that X is a subspace. Okay. So I will leave it as an exercise. So we already have a theorem when the subset is a subspace. First we need to check whether X is non-empty or not. If it is non-empty, we should see whether CA plus B belongs to X for all AB in X and C in real number, scalar. Okay. So just see that condition, whether it's satisfied or not. Obviously, it is a subspace. Just write it in detail. Okay. Or anyone has a doubt in this? Like I have already solved for the symmetry case. If you have doubt, you can ask. Okay. Otherwise, we will see what is the dimension of X. Now, okay, maybe you can just very quickly you can just try on a paper what can be the dimension. As in the earlier case, we have given ABCD equal to ACBD, and we solved to check how many variables are involved in that. In the same way, very quickly you just write A equal to ABCD and equate it to minus of A transpose. Okay, take the A transpose and take the minus of that. So while equating, you will get some condition. So equating each of the coordinate, you will get some condition, and using that condition, you can see how many variables are remaining to describe all X. Okay, so I just want you to try this once now. Just write A, equate A equal to minus A transpose, and see how many variables are remaining. Okay, take 1 or 2 minutes and solve it. Okay, dimension 3. It is not 3. Okay, you can just redo it maybe. Maybe some calculation error may be there. Just redo, like just write A equal to minus A transpose and see. Or, okay, I will just write it. You just follow with me. A equal to, or do you need some time to check this? If anyone wants some time, I can give some more time, or we can solve it together. Okay, let's solve it. A equal to minus A transpose. Here A equal to AB, CD. So A transpose is interchanging rows and column. and minus A transpose means taking a negative sign. Okay, so what we will get here? A equal to minus A. First entry equating means A equal to minus A, and B equal to minus C, C equal to minus B, D equal to minus B. Okay, now A equal to minus A. What does this means? When will A equal to minus A? If A equal to minus A, what is A?
0.
Yeah, obviously A equal to 0. A equal to 0 and D equal to minus D. So D is also 0, right? Okay, so we got A equal to 0 and D equal to 0. The only two conditions remaining is B equal to minus C and C equal to minus B. Basically, both these conditions are same. B equal to minus C and here minus C equal to B. Both are same, right? So we can write it as a single condition B equal to minus C. Okay, now we are substituting these values back to this A. So what we will get is A equal to, the first element A equal to 0 and D is also 0. And if we are fixing B equal to B, then C equal to minus B. That is what this condition says, B equal to minus C or C equal to minus B. Okay, clear? So if a matrix A is a skew symmetric matrix, or if A belongs to the set X, then the general form of A, or it will be like this. Okay, now anyone can guess what is the dimension of A? Sorry, dimension of X.
2, ma'am.
2? How many variables?
No, 1.
Okay, 1, because only one variable is there. Here we can write it as B into 0, 1, minus 1, 0. Okay. That means only one matrix minus 1, 0 is involved to span all the matrix in the X. That means it is enough to span all the skew symmetric matrices, and it is a non-zero metric. Obviously, it is a linearly independent set. Okay. So, B equal to 0, 1, minus 1, 0. Say basis for X. So dimension of X is 1. Okay, here actually you can notice that dimension of symmetric matrix is 3 and the dimension of skew symmetric matrix is 1. So 3 plus 1 equal to 4, which is the dimension of full matrix. So like it is not a coincidence actually. Maybe the details you will study later. Okay. So is there any doubt in this first question?
No, ma'am.
Okay. So then let's move to the next problem. The question is V equal to R2. The vector space is given as R2 and it is over the field R. And the addition, vector addition, usually we will define the as a usual addition. Here the addition is defined as from the vectors P cross V to V, and the scalar multiplication from F cross V to V is defined as so actually the addition is the same as the usual addition, the component wise addition. Okay, but the multiplication Scalar multiplication is defined as so the question is whether this V is a vector space over R or not. So the addition is given as xy plus x1 y1 equal to x plus x1 y plus y1, the component wise addition. And the scalar multiplication, alpha is an element from R and xy is an element from R2. The scalar multiplication is defined as, for the first component, just x, and the second component, it is multiplied with alpha y, with alpha, okay. So the question is V a vector space over R? So in order to be a vector space, it should satisfy all the conditions of the vector space. For that, the first one will be R2 with this operation plus is an abelian group. Here we can see that this addition is actually the usual addition. So under usual addition, obviously it is a R2 is a group, right? Abelian group, like commutative also. So R2 plus is an abelian group. Is this statement clear for everyone? It is like we have studied the group theory also. Okay, this is fine, right?
Yes, ma'am.
Okay. Now, so the only thing we need to check is the properties which are related to the scalar multiplication. So, do you think whether all the property defined in the vector space is satisfied for this particular scalar multiplication? Anything fails to be satisfied? Can you think of all the properties? Let me write alpha 1 plus alpha 2 of xy equal to alpha 1 xy plus alpha 2 xy. It should be satisfied, right? Okay, here this plus is, okay. This condition, is this condition satisfied or not? This is a question mark, okay. This is one of the condition of the scalar multiplication. So that if it is satisfied, like it is one of the condition, so that it should be there for V is a vector space. Now, let us see what is LHS. Okay. Here the multiplication is this multiplication. What is LHS? The definition is given here. What is LHS? Please expand this using this definition and tell. Now, alpha 1 plus alpha 2 is a single scalar. Like I'm taking two real numbers, alpha 1 and alpha 2. Okay. And adding that alpha 1 plus alpha 2. That into xy. What will be it by definition?
X comma
X comma
in bracket alpha 1 plus alpha 2 into y.
Yes, alpha 1 plus alpha 2 y. So this is just using the definition of the given scalar multiplication. Now, what will be the RHS? What will be alpha 1 xy? Again, here
X
it is.
comma alpha 1 y.
Yeah. Here the multiplication is given as in the definition. So x comma alpha 1 y plus x comma alpha to y, right?
Yes, ma'am.
So what will be this? This is the addition. So this is usual addition only. Okay, we have defined the addition as the usual addition.
2x, comma, alpha 1, y plus alpha 2 y. We can take y as a common, alpha 1 plus alpha 2 y.
Yes, correct. So what we will get is 2x alpha 1 plus alpha 2 y. So this LHS and RHS are different, right? Here it is x, here it is 2x. Okay. So LHS not equal to RHS. So this condition is not satisfied. So it is not a vector space. Again, if we are just getting some R2 or whatever the space, whether it is a vector space or not, it depends on the operations also. Like in general, if we are getting some R2, we will use the standard operation. If the operation is specified, we should check whether it is a vector space under that given operations. Okay. Is this fine for everyone? Any doubt in this? Like actually, there can be other condition also which is not satisfied. Maybe you can go through all the condition and check what are all satisfying, what are all not satisfied and all. So this is one condition, it is not satisfied. So only one condition is violated. So we can say this is not a vector space. Okay, shall we move to the next problem if you don't have any doubt? Now, let's go to a very trivial question. Actually, it is covered in the class. And if a vector space V is given, whose dimension is n, and W be a and cardinality of W is given as P. Okay, so we have 4 options. Okay. So the options are here V is a vector space which is having dimension n, and W is a set, like we can say a subset in V, and the number of elements in W is P, and given that W is linearly independent. So the question is to find the relation between P and N, whether P is less than N or greater than.
It is B answer.
Okay, answer B. Okay, this is very trivial question. Answer is B. Because the reasoning is W is linearly independent subset, right? So dimension of V equal to n means the number of elements in the basis of V is n. Okay. So any basis is actually a linearly independent set. And in fact, a basis is the maximum linearly independent set. So if we are taking any linearly independent set, then the number of elements in the linearly independent set will be less than the number of elements in the basis. So P will be less than or equal to n. So only thing is basis is the maximum linearly independent set. Actually, the very explicit proof of this is given, I think, in the lectures. You can just go and check. So I think no need of more explanation. Is this fine for everyone? This question? Any doubt in this question?
No, madam.
Okay. Now, So here a set, sorry, in R3. Okay. A set 101, 110, ABC in R3, it's not R2. R3 is given, and we need to find the condition on ABC such that it is a linearly dependent set. Okay. So, what is linearly dependent means? We should be able to write it as a linear combination like K into K1 into 101 plus K2 into 110 plus K3 into ABC equal to 0, 0, 0, such that one of the K is non-zero. Okay.
Madam, answer is A.
Are you sure?
You tried, I'm just guessing. Because it is linearly dependent, so some element is dependent on other. That's why I'm telling.
Okay, if answer is A. Okay, what is the justification for like if A plus B equal to C, then it will be linearly dependent? Now, for example, I am taking. Okay, first let me give an example. I am adding this element 10 plus and 110. Okay, two elements are there 101, 110. And I am taking it as, okay, it is 2, 1, 1. Okay. Now, let ABC equal to this 2, 1, 1. Clear? Now, we can see that here A plus B equal to 2 plus 1, which is not equal to C, right? But it is linearly dependent. Here, 101, 110, 211 is linearly dependent. Why it is linearly dependent? This 211 can be written as the linear combination of these two. Otherwise, we can say 1 times 101 plus 1 times 110 minus 1 times 211 equal to 0 with the coefficient 1, 1 minus 1 are non-zero. Okay. So that condition says that these three elements are linearly dependent. So in our question, what they are asking is the necessary and sufficient condition for this to be linearly dependent. But here, the set 101, 110, 211 is linearly dependent set, but A plus B equal to C is not satisfied. That means 2 plus 1 equal to 1 is not satisfied. But we can see the condition B, A minus B equal to C, it is satisfied. So the possibility is for B. Okay, because the third condition A plus B plus C equal to 0, 2 plus 1 plus 1 equal to 4, not equal to 0. This is also not satisfied. So possibilities for B, not for A and C. With one example, we are able to say, but we will say it in general. Is that fine?
Yes, yes.
Okay. So let us see how it actually works. So in general, I am taking as just a linear combination of 101, K1 into 101 plus K2 into 110 plus K3 into ABC equal to 0, 0, 0. Okay. So what I will get is K1 plus K2 plus a K3. K1 plus K2. I'm just expanding these terms equal to 0. So I'm just adding all the three coordinates. Okay. So I will get this, and next in the next stage I will write it in the matrix form. Okay. So what I will get is 1, 1A, 0, 1B, and 1, 0, C into K1, K2, K3. So you know how to write like this, right? Okay, like this you can write here. Means K1, K2, K3 I am taking as the variable matrix, and just the coefficient 1, 1A into that is K1 plus K2 plus K3. This is the first equation. 0 K1 plus 1 K2 plus B K3. It is the second equation. Likely the third equation. And in the right hand side it is 0. Okay. Now, what we are having is this is equal to 0. Okay. Now, this matrix C, see the 1, 1A, 0, 1B, 1, 0, C. Suppose it is A. If determinant of A equal to 0, this K1, K2, K3 has a non-trivial solution. Okay. For example, okay. Suppose if determinant of A is non-zero, that means A inverse existed. Correct? So, we can multiply A inverse here in this side. So, what we will get is A inverse into this A is identity. Here also we will multiply A inverse. So, A inverse into 0, 0, 0 means it is a 0 matrix. So, what we will get is K1, K2, K3 equal to 0, 0, 0. This case happens when determinant A is non-zero. Okay, that means if determinant of A is non-zero, we will get K1, K2, K3 is 0, 0, 0. That means the coefficient is 0, 0, 0 means it is linearly independent. But what we want is linearly dependent. So we should start with the determinant of A equal to 0. Is that reasoning clear for everyone? Why this determinant of A should be equal to 0? Any doubt? Do you want me to repeat? If you have doubt, you can ask. Like maybe I can repeat. Clear for everyone?
Yes, ma'am.
Okay, okay. No, okay. Okay, I will repeat once again. What we are having is A into some K1, K2, K3 equals 0, 0, 0. Okay. So this K1, K2, K3 we can see. We have taken this K1, K2, K3 as the coefficient of these three vectors that is given to us. Okay. So finally we are having A into K1, K2, K3 equal to 0, 0, 0. Suppose determinant of A not equal. Suppose determinant of A is not equal to 0. Then what we can say is A inverse exists, right? Now what I will do is I will multiply star with A inverse on the left side. Okay, I will multiply this A inverse on both sides. Okay, left side means left side of equality, like in both sides. Okay, A inverse A into K1, K2, K3 equals A inverse 0, 0, 0. So here what I am writing is multiplying A inverse on both the sides. So A inverse A into K1, K2, K3 equal to A inverse 0, 0, 0. And here A inverse A is identity. So identity into this matrix obviously it is K1, K2, K3. Here A inverse into the 0 matrix. So in this side it is 0. So what we are getting is K1 equal to K2 equal to K3 equal to 0. That means the given set is linearly independent. Okay. So we are starting with the determinant of A not equal to 0 and A inverse exists, and we are getting K1 equal to K2 equal to K3 equal to 0. Okay. So in the expression here, okay, we are writing the linear combination of these three vectors K1, K2, K3, and we got these are equal to 0. So if all these are 0, what we can say it is linearly independent. But what we want is linearly dependent. So the problem is we should start with the determinant of A is 0. If determinant of A equal to non-zero, we are ending with the K1, K2, K3 equal to 0. But in question, we need to find the condition for the dependency. So we will start with the matrix is, the determinant of the matrix is 0. Okay, is that fine now? So what we can say is determinant of A should equal to 0. And now what is the matrix A? 1, 1 is. So what we need to find is the condition on A and ABC such that this determinant of the matrix A is 0. Now we can just see the determinant. So whatever the condition we are obtaining, that will be the condition for the linear dependence of the given vectors. Okay. So we will just write it as 1 into C minus, okay, I'm just finding the determinant.
It's green.
Okay, A minus B.
Favorite.
Okay. Okay, so this is the second condition given. I'm taking A and B to one side and C to other side. So what we will get is A minus B equal to C. So this is the condition in given. Here A minus B equal to C. So when we took one example, here 2, 1, 1 I have taken. So we got this 2, 1, 1 satisfy A minus B equal to C, right? So in general, we got the condition A minus B equal to C. So answer B is the correct answer for the dependency. Is that okay for everyone?
Yes, ma'am.
Okay, if you have doubt, you can ask us. Otherwise, we can move to the next problem. Any doubt in the last question?
No, ma'am.
Okay. Now, the next question is, there is a set of statement. So we need to check what are all the correct statement. Okay. So here we have three statements. We need to check which one is not true, the wrong statement. Can anyone say which one is a wrong statement among all these three?
A.
Yeah.
A is wrong.
Yeah. Can you give the explanation for that why A is wrong?
Because R complex number is not the subfield of real number.
Okay, so like vector space means it should satisfy the given condition. That is correct. I mean, I just want the proper explanation. Which condition is not satisfied? Like,
Ma'am, there is a scalar alpha in the complex field and the vector in the real field, the multiplication not in the real field.
yes, correct. Because if R is a vector space over C, C is a field, and if we are taking an element alpha from C, then alpha into R means an element R in R. Alpha into R should be an element of R. Okay. So here if I am taking, if I belongs to C, this I is a scalar. Okay. Is a scalar, and then I am taking 1 is an element in R. Here R is the vector space means this 1 I am taking is a vector. Okay. So the scalar, under the properties of scalar multiplication, this scalar into this vector should be the element of R. Okay. But here I into 1 equal to I, which does not belongs to R. So R over C is not a vector space. Okay. In general, if we are having one field F, and which is a subfield of a field F1, then F over F1 will not be a vector space. Here R is smaller than C. We can say R as a some kind of subset of C, right? So R over C is not a vector space. In general, it is true. Like the smaller one is not a vector space over the bigger one. Now, what about B and C? Is the statement true or not? So the first statement A is false.
True.
Yeah. Here B and
Both
C.
are vector space.
Yeah, both are vector spaces. Here C over R, because C is the bigger space. So whatever the scalar we are taking, I into some complex, like not I, any scalar R in R into some complex number is again in a complex number. And C under addition is a abelian group, and all the conditions will be satisfied. This is true for this R is a vector space over Q, because Q is smaller than R. Okay. So in this case, if this one, the vector space is bigger than the field, then obviously it will be a vector space. In a opposite way, if it is the smaller field, it is not a vector space over the bigger field. Okay. So let's go to the next problem. Okay, now the question is, so we have already seen C over R is a vector space. What is the dimension of C over R? So C over R is a vector space. Now the question is, what is the dimension of C over R? Any answer? To find the
2n.
Can you repeat?
2n.
2n. C over R. Not Cn or Rn. Like here I'm just dealing with C and R.
2.
Okay, 2.
2,
So
2.
yeah. So to find the dimension, basically what we will do is, whatever the vector space it is given, we will write it in a general form. Here what we can see is the set C, like the vector space C is set of all A plus IB such that A and B are from the scalar field R. Okay. So what we can say here, this is actually A into 1 plus B into I with the A, B in R. So what it is happening here is the 1, okay, 1 and the I are two elements in the basis. So B equal to 1 I forms a basis for C. Why it is a basis? Obviously, it is linearly independent, right? Any doubt this P is linearly independent?
No, ma'am.
Okay, just I can give one explanation. So C1 into 1 plus C2 into I equal to?
Yes, ma'am, it is linearly independent.
Yeah, it is linearly independent because if I am equating it to 0, both C1 and C2 equal to 0, correct? So it is linearly independent. And obviously, it spans all the complex numbers because A plus IB form. Okay, it spans all the complex numbers. So it forms a basis. So what here it happens is the 1 covers all the real part actually. And I covers all the complex part. And taking the linear combination means it covers all the complex numbers. Okay. So since B has 2 elements, we can say dimension of C over R is 2. Okay. Now, coming to the next question. What is the dimension of C over C? Earlier, the field was C over R. Okay. Now, I'm just modifying the question. What is the dimension of this C over the complex field C? What is the answer?
One.
Yes, it is 1 because just one element, say 1, it is enough to generate full C, right? An element, whatever the element A plus IB, like here I am taking this A plus IB belongs to C is a scalar. Okay. And 1 in C is a vector. Okay. So this A plus IB I am taking from the field C and 1 I am taking from the this vector space C. Okay. Now I can take A plus IB, the scalar into the vector 1. What I will end is A plus IB. Now this A plus IB is a vector in C. It's a vector. Okay. So just the element 1 is enough to generate all elements in C. And the set 1 is linearly independent. So set 1 forms a basis. Actually, not just 1. Any element, like we can say 2 also. Okay. Any element is a basis, forms a basis for C. So dimension of C over C equal to 1. Now, what is the dimension of R over R? The vector space R over the field R. You can just think the same logic. I mean, what we have done for C, the
One,
same.
one, ma'am.
Yeah, the same is happening here for R also. Like I'm taking any element in R, say some C in R, I can write it as C into 1. Okay, so the element 1 itself generates or spans whole R. So dimension of R over R is also 1. Okay, in general, if F is any field, okay, is any field, dimension of the vector space F over the same field F is 1. Okay, any element, any non-zero element will generate the whole field. Is this fine? Now, one more question. Dimension of R2 over R. What is dimension of R2 over R? Dimension of R2 over R means number of elements in the basis. Like the number of elements, linearly independent elements, which can generate the whole R2. So you can see what is the general form of an element in R2. How many variables are involved in that?
2, ma'am.
2, yeah. Because R2 means set of all A, B. That we can write it as A into 1, 0 plus B into 0, 1. So this 1, 0, 0, 1 is the basis. 1, 0, 0, 1 is the basis. Okay. Now, what will be the dimension of Rn over R?
N.
Okay, it will be N. So it is also the same reasoning, 1, 0, 0, 0, etc. 0, 0, 1, 0, 0, etc. Like that, n elements we will have, that will forms the basis of Rn over R. Okay. Now, let's see, number of describe all possible subspaces of R2. We know what is R2. R2 is the R cross R the plane. And like just I'm saying R2 means it is over the field R. Okay. So here the question is number of possible subspaces of R2. Okay. Now we already know dimension of R2 okay, this we have already seen. Dimension of R2 is 2. Now, if W is a subspace of R2, okay, I'm saying W is a subspace of R2. Now, what are all the possible dimensions of W? So,
0, 0.
yeah, 0 is a possible dimension. Then
1, 1.
1 is a dimension.
That's all.
2, like R2 itself is a subspace of R2 means 2 is also possible, right? In that sense.
Okay.
Okay. So obviously W is a subspace of R2 means the dimension of W will be lesser than the dimension of R2. And the dimension will always be positive, like greater than or equal to 0. Okay. So the possible dimensions are 0, 1 and 2. Now, what is the subspace having dimension 0? The subspace of R2 which is having dimension 0.
Zero comma zero.
Yeah, the trivial subspace 0. Okay, like you can take it as a convention. Means the subspace means like dimension 0 means, sorry, dimension n means there are n element in the basis. Dimension 0 means there are 0 element in the basis. Actually, it does not have a basis. Like if it has a basis, that basis is linearly independent, right? And the possible element in the basis of this is the 0 itself. But 0 is not linearly independent. 0 can be written as 0. 0 can be written as 0 equal to some 1 into 0 we can write it. Where 1 is a non-zero coefficient. So this, if 0 belongs to a set, it is always linearly dependent, not independent. So it is like, so as a convention we can take it as the dimension 0 is subspace is always the trivial subspace. Now we will move to the subspace having dimension 2. Okay, later we will go to dimension 1. What is this subspace having dimension 2? I already mentioned that.
One zero zero one.
No, what is that subspace I am asking? Like that, like dimension 2 means that is the basis, right? 1001, it is a basis. So it generates the subspace. What is that subspace? R2. Okay. Dimension 2 means 2 elements, linearly independent elements generates. Okay, this 1001 we can say. It generates the whole space R2. R2 itself is a subspace of R2. Correct? So we can say there is only one subspace having dimension 2. Now, what are all the subspaces? Now I am writing it as subspaces. That means there are various subspaces, not just one subspace. Okay, subspaces having dimension 1. Can anyone think what will be the subspace having dimension 1? Maybe you can think geometrically what is R2 and what can be the dimension, like what can be the subspace of dimension 1. Or you can think like analytically, like dimension 1 means only one linearly independent element generates the subspace. So can you just think on that and can you say what are all the possible subspaces with the dimension 1?
0 comma 1 and 1 comma 0.
0
R.
R. Okay. R actually, R means set of all elements like
One in that set. One.
Straight line.
yeah,
No,
straight.
it passes through origin.
Yeah, straight lines passing through the origin. There are infinite number of straight lines passing through the origin. Actually, that are all the subspaces of dimension 1 in R2. Okay. Now, all the straight line passing through origin. So, okay, let me give this geometrically. In fact, okay, someone told R as a subspace of R2. Actually, R is not exactly the subspace of R2 because R2 means set of all two tuples. R2 contains set of all elements of the form AB. Correct? But R contains just elements A. But if you are identifying R as set of all A0, okay, the real lines in R2 is actually set of all like 1, 0, 2, 0 like that, right? So in that sense only we can say R. Like in general, R is not a subset of R2. Okay, if you are identifying R like this, then only we can say R is a subspace. Okay. Now, what we want is, in a subspace, always we want a zero element. Okay, without zero element, we cannot have the subspace because the additive identity 0 should be there. So this 0 should be there always. Okay. Now, the subspace having dimension 1 means there exists an element C which generate pole. Okay. So, if W, dimension of W equal to 1, suppose. Okay. Then, basis of the W is some C with the C is non-zero. If C equal to 0, it will like only set to 0 is remaining, right? If I am taking some C non-zero, then what I will do is, I will take all the linear combinations of C to get the W. That means W equal to set of all Kc. So K is some scalar into C, such that K in R. Okay. So this is actually in the form y equal to mx, the straight line form. That is, the elements of W are all Kc, like set of all y equal to Kc, something like this. Okay. So it is in the form of the straight lines which is passing through the origin. Okay. Like this. If I am taking some C here, Kc will be here. So this straight line, the same way the other straight line. All the straight line passing through the origin are the subspaces of R2 with the dimension 1. So in the same way, let us quickly go. What are all the... So geometrically only I want the answer. Possible subspaces of R3. So first of all, dimension 0 means trivial subspace. So we don't need to repeat again. And dimension 2 means, dimension 3 means it is R3. Now remaining is dimension 1 and dimension 2. Dimension 1 you may guess what are all the subspaces. And dimension 2 also you can say like... So, okay, first of all, what is the subspaces having dimension 1 in R3? Dimension 1 means we are starting with one element C and all the multiples. So what is that?
Zero, 1, comma 1, like that.
No, I'm asking like here we know what are all the dimension 1, right? In the earlier question, we know what is dimension 0 subspace. It is 0. And dimension 2 subspace. In the earlier case, dimension 2 subspace means R2. And dimension 1 subspace means all the straight lines. Okay.
It also passes through origin.
Yeah. Here also what is the dimension 1 means? Straight line, right?
Yes.
Dimension 1 means the bases have only one element. And that one element generate the whole space. For example, if the basis is C, okay, the set C generate all element means all the multiples of C. Okay, all the multiples of C means just through the straight line only that multiple goes, right? So, all the straight line, and it should pass through the origin. All the straight line passing through origin. Now, can you just think about what will be the subspace having dimension 2? Dimension 2 means it is generated by two elements, like two linearly independent elements. What will be that?
Then there should be a one element is zero element. So it also passes through origin.
It should passes through origin, correct? So geometrically, can you think what will be that set or that subspace? Now it is not line. Okay, there are two elements which generates the subspace of dimension 2. Okay, so it is not. Any answer?
No, set of all plane
Yes.
passing through origin.
Yeah, now it is the set of all planes passing through the origin. Like we are going from one dimension to another dimension. So the one dimension is straight line. And the second dimension going, dimension 2 means the next dimension we are jumping. So straight line, next dimension is set of all planes. And the next dimension means the space R3 it will come, right? So dimension 2 is all the planes passing through the, like to draw that it will be difficult, like maybe you can passing through origin. Okay, so for example, if I am taking element 1 0 0 and 0 1 0, these two are elements of R3 and these two are linearly independent, and let me take W as the span of 1 0 0 0 1 0. Okay, so what is this? This dimension of W is 2. Because I am taking two linearly independent set which spans W. So W has dimension 2. And you can easily see that it is a plane. It is a plane, like the Z coordinate is 0. Okay. So only X coordinate and Y coordinate varies. So all the linear combination means it covers all the XY plane. It does not go to the Z plane because Z plane is always like Z coordinate, because Z coordinate is always 0. So it is actually the XY plane. XY plane in R2. Okay. In the same way, whatever two linearly independent set you are taking, some plane you will get in R3 which passes through the origin. Is that clear for everyone? Like that we can extend to Rn also. Any doubt in this question? Last question. If you have doubt, you can ask now itself.
No.
Okay. No, okay. The dimension of so the question is, we have given a subspace of R5. Means here we have 5 coordinate A, B, C, D, E. And the condition is A plus B plus C plus D plus E equal to 0. Okay. So the question is to find the dimension of this subspace. So let us call it as W. Just looking at the condition only, you can easily say what is the dimension. Can anyone guess
4.
what is? Oh, sorry.
4.
Yeah, it is 4. Dimension is 4. So as I already told, using the condition, we need to check how many variables, independent variables we can take. Like we need to generate whole subspace. So here actually it is AB, the general form it is ABCD in R5 with the condition A plus B plus C plus D plus E equal to 0. Actually, one of the variable we can write in terms of all the 4 variables. Nothing else we can do. For example, E, we can write it as minus of A plus B plus C plus D. So instead of E, we can write like that. Okay. So we only need 4 variables to get whole W. This is actually A, B, C, D. And instead of E, we can write minus A plus B plus C plus D. Okay. Set of all ABCD. It is like this. Like these ABCD are elements in R. Is this clear? So only 4 variable means dimension of W equal to 4. So if you have this kind of question, you just need to write like all possible things. Means some variable, if we can write it in terms of other variables, just write like that. And how many distinct variables are there? That will be the dimension of W. Is this fine? Is this question fine for everyone? Answer? Okay, shall we move to the next question? So we have one statement. We need to check whether this is true or false. So it is given 2 vectors are linearly independent. So the question is whether one of them is a scalar multiple of other. The statement is, it says one of them is a scalar multiple of other. So,
True, ma'am.
yeah, true. Can you give the explanation? Suppose alpha and beta are linearly dependent vectors. Now, linearly dependent means what we can say, like by definition, what is that means? What is the definition of like linearly dependent means? There exists some non-zero coefficient C1 and C2, like one of them is non-zero. There exists C1, C2 with at least one of C1 and C2 is non-zero. That is either C1 or C2 or both is non-zero, and such that C1 alpha plus C2 beta equal to 0. These are linearly dependent means we can find some non-zero, either C1 or C2, such that C1 alpha plus C2 beta equal to 0. So we have 2 possibilities. Either it can be C1 equal to 0. We don't know about, sorry, C1 is non-zero. We don't know about C2. Okay, C2 can be 0 or non-zero, whatever. If C1 is not 0, what we can write? Alpha equal to minus C2 by C1 into beta. Okay. So here C1 non-zero condition is required. That is why we can take this C1 to denominator. If it is 0, we cannot do like this, right? So that is why C1 not equal to 0 is required. So alpha is a scalar multiple of beta. Okay, some scalar minus C2 by C1 into beta is alpha. And in the same way, if C2 is non-zero, we know at least one of them is non-zero. Okay, so if C2 is non-zero, what we can write? Beta equal to minus C1 by C2 into alpha. In that case also, some scalar multiple of alpha. Like in both cases, we can see one of them is a scalar multiple of the other one. Correct? So, statement is true. Is this proof clear for everyone?
Yes, ma'am.
Okay. So the next question is to find the coordinate of a given vector. Here, given a vector 1, 0, 1, we need to find the coordinate of this vector in the basis, this A, and second in the basis B. This is two questions, okay? So, what does mean by coordinate of vector in a basis? Do you remember what is that mean by the coordinate of vector? So what actually says is like if we can write 1, 0, 1 equal to, okay, I will start with the first one, okay. A into 1, 0, 0 plus B into 0, 1, 0 plus C into 0, 0, 1. Okay. If we are writing like this and solving for ABC, so whatever we are getting, this ABC is the required coordinate corresponding to the given basis 1, 0, 0, 0, 1, 0, 0, 0, 1. Required coordinate. Clear? Here in the first question, to find the coordinate, it is easy. Okay, what will be the coordinate in the first case? If the basis is like this and the vector is like this, what is ABC? This is just like, just equate these two sides. I mean, just expand this and just see what is ABC. It is very trivial thing to write.
A equal 1, B equal 0, C equal 1.
Yeah, this is just we are expanding means what we will get A. Like here, this side we will get first
A plus
coordinate
B
yeah.
plus C.
Here we will get first coordinate is A plus B into 0 plus C into 0. That is A. Second coordinate is B. And third coordinate is C. So basically, what we can say 1, 0, 1 equal to A, B, C. So the coordinate ABC itself is the vector 1, 0, 1. But it is not true in general. I am taking another basis here. Now what we will see what is the coordinate in this case. Again here we will write A into 1, 1, 0 plus B into 2, 2, 0 plus C into 0, 1, 2. Here actually just by looking at this we cannot say like, so let us just solve these three equations. So what
B into 0, 2, 0, 0.
Sorry, can you repeat?
B into 2, 0, 0. You return 2, 2, 0.
Okay, 2, 6, sorry. B into 2, 0, 0. Okay. So we will solve it, okay. Here what we will get is, if we are just expanding this side, what we will get? A plus 2B plus 0. Okay. Second term is A plus 0B plus C. A into 0 plus B into 0 plus C into 2. So it is 2C. Okay. Now we can equate the left and right side. So here we have only one C variable, 2C. So 2C equal to 1 implies C equal to 1 by 2. And next one is, we got C value. Next we will equate A plus C. What is A plus C equal to 0? And A equal to minus C, which is equal to minus half. Next is A plus 2B equal to 1. And so what we will get? 2B equal to 1 minus A, which is equal to 3 by 2. That is, okay, 1 minus A means 1 minus 1 by 2, it is 3 by 2. And that implies B equal to 3 by 4. Okay, so the coordinate ABC will be equal to, A value is minus half, B is 3 by 4, and C equal to half. Clear? So you can just put the value ABC back and you can check whether that linear combination gives the 1, 0. So this is the coordinate vector corresponding to the second basis. So corresponding to first basis and corresponding to second basis, we have different coordinate vector, right? So it depends on the basis that what we are taking. Fine. Any doubt in this one?
No, ma'am.
Is the dimension of so the question is, what is the dimension of the vector space of all polynomials of degree n over R? Okay. So we know what is the polynomial. Polynomial will be in the form a0 plus a1x plus a2x square plus etc. plus an x power n, because degree is here. Okay, so we need to go to up to n only. And over R means all these coefficient a0 to an r belongs to the real numbers. So the question is, if V is the vector space of all this kind of polynomials. Okay, then what is the dimension of V? So like dimension of V means first we need to see what is the basis. If we get the basis, we can say what is the dimension. So what can be the basis? Like which set can generate all the polynomials like this? Any idea?
Ma'am, 1x squared up to x power n. There are n plus 1 elements generate the vector space. So dimension is n plus 1.
Dimension will be n plus 1 because it starts with 1 and it ends in n. So if I am getting a general polynomial a0 plus a1x, so here a0 plus a1x plus etc. an x power n is the general polynomial. This polynomial is actually spanned by this set. I am just multiplying with the constant a0 into 1 plus a1 into x plus a2 into x square plus etc. an into x power n. So the span of this is actually the set of all polynomials. So what we can say is span be equal to V. Okay. So now this is not enough. To prove V is the basis, we need to say V is linearly independent also. So it may seem a bit complicated, but it's actually very simple. Like just by looking, actually we can say it is linearly independent because like, okay, we will prove it. To prove B is linearly independent. Okay, so what we will start is, we will take a linear combination C0 into 1 plus C1 into x plus etc. plus Cn into x power n equal to 0. Okay. We are equating that to 0 polynomial. And if each of the Ca equal to 0, then it is linearly independent. Otherwise, it is linearly dependent. Okay. Actually, by fundamental theorem algebra, okay, suppose f of x equal to C0 plus C1 x plus etc. plus Cn x power n. Okay. Now, if Ca equal to 0 for all I, then what we can say? F of x is identically equal to 0. Okay, if I am getting all Ca equal to 0, f of x is identically equal to 0. And if Ca equal to 0, we can say it is linearly independent. Also, B is linearly independent. Okay. If Cj not equal to 0, for some j, Cj is not 0. Then f of x is a non-zero polynomial. Okay. F of x is actually non-zero polynomial. And it can have degree at most n. Okay, we don't know what is Cn. If Cn equal to 0, its degree is less than or equal to n minus 1. Okay. Here Cj is non-zero means minimum degree j is there. Okay. So, also, what is the maximum possible zeros of f of x? F of x is a non-zero polynomial of degree some n. We can say it is n. We don't know what is j. Cj is non-zero only we know. We don't know about this. Anyhow, f of x is a non-zero polynomial of maximum degree n. So, this f of x can have at most n roots or n zeros. Correct? If second degree polynomial means it can have at most 2 zeros or 2 roots. So nth degree polynomial can have at most n zeros or n root. So what it is saying is this f of x equal to C0 plus C1 x plus etc. Cn x power n equal to 0 for some maximum n values of x. There are x1, x2, etc. xn are roots. Say x1, x2, etc. xn are possible roots. Okay. So what we can say, f of x1 equal to f of x2 equal to etc. equal to f of xn equal to 0. And for all other f of x, this f of x not equal to 0. For all x not equal to xi, I equal to 1 to etc. n. Other than this x1 etc. xn value, this f of x is non-zero. But here we are getting a contradiction because what we are having is f of x is C0 plus f of x is C0 plus C1 x plus etc. Cn x power n is identically equal to 0 for all x. This is not possible because if f of x, like this contradiction happens because we have taken for some Cj, it is non-zero. Okay, that is why we are getting f of x is a non-zero polynomial. But what we should have, if f of x is a non-zero polynomial, this equal to 0 for only finitely many values of x. But we should have this equal to 0 for all values of x. So only possibility is Ca should be equal to 0 for all I. Okay. So what our conclusion is? Ca should be equal to 0 for all I. That means the set B, 1, x, etc., x power n is linearly independent. It may seem a bit complicated, but it is just like just we are using the fundamental theorem of algebra, like the number of roots of a polynomial is n only, like at most n. Okay. Is this clear for everyone? Any doubt? Do you want me to explain again? At any point, if you have doubt, you can ask. Any doubt in this solution?
No, ma'am.
Okay. So other than this, like in any question, if you have doubt, you can ask now. Otherwise, we can stop the meeting. So if anyone has doubt, you can we can go through that. Okay, if you don't have doubt, you can leave the meeting also. So shall I stop sharing now?
Yes, ma'am.
Okay, then let's stop the session. Yeah, thank you everyone for attending the session. So we will meet in the next week again.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
Okay, thank you all.